Assalamualaikum and very good morning. My name is Farouq bin Ahmat and my presentation title is Feasibility Study Recovery of Lanthanum, Cerium, Praseodymium, Neodymium and Yttrium from Malaysia saprolite by HD, EHP, HCl cascade fractional solvent extraction. So for introduction, Malaysia rare earths mostly occur in the phosphate minerals such as xenotime and monazite. According to Academic Science of Malaysia 2014, it is estimated Malaysia has around 30,000 to 43,000 ton of rare earth element, and the elements are associated with the byproduct of tin mining and ion extraction clay. The modern industrial technology to extract the rare earth element from the deposit is performed through solvent extraction because the technique is very efficient and its ability to extract high purity rare earth element. The selectivity behavior of solvent extraction is relying on three attributes: the nature of solvent and aqueous phase, a strong interaction among the components of the system, and physiochemical similarity among the lanthanides. A cascade fractional solvent extraction is a multi-stages solvent extraction where the feed is introduced at the final extraction stage while the organic and scrubbing are introduced at the initial extraction stage and final scrubbing stage respectively. The advantage of cascade fractional solvent extraction is the process can produce simultaneously high purity and high recovery rare earth element. The process setback is the difficulty in quantifying and predicting the process outcomes due to the poor understanding of strong nonlinear effect. The rare earth element concentration data was acquired from the work of Toha and Yunus 2020, and then the sample was collected from Malaysia saprolite layer at Tengah Island, Johor. The table shows the element concentration and their category, but in this study, the focus is only on La, Ce, Nd, Pr, and Y. The methodology for the whole study is summarized by the flowchart. For result and discussion, the graph shows the comparison of rare earth element concentration found in Malaysia saprolite, enriched Canada Nachalacho, and mountain pass carbonatite. The graph indicates the amount of rare earth element found in Malaysia saprolite is at par with other major deposits, even though the amount of rare earth element in Malaysia saprolite contain a slightly lower concentration of rare earth element than found in enriched Canada Nachalacho, but it is significantly higher than the amount found in the mountain pass carbonatite with the exception of PR. In this case study, only the top 5 elements found in Malaysia saprolite, which are La, Ce, Nd, Pr, and Y, were investigated. The table shows the comparison of rare earth concentration in Malaysia saprolite and mountain pass carbonatite. The figure shows the proposed flowsheet cascade fraction solvent extraction from the beginning until we acquire the La, Ce, Nd, Pr, and Y. The table shows the process parameter for each simulated separation circuit. We can see that from the table, feed composition, product purity, extraction recovery, separation factor for each circuit, maximum extraction, S naught, maximum scrubbing, WA, flow ratio, extraction stage, the scrubbing stage, and then the total stage, which is extraction stage plus the scrubbing stage will be equal to the total stage. The table shows the simulated separation property. The SO and WA value are correlated with the separation stage numbers. When the value of SO and WA reduce, the number of separation stage reduces, and vice versa. The high value of EM is preferred to achieve high purity of B and less separation stage number. But with the increase of EM, JS also increase. With the increase of JS, the daily output for the same size equipment will be significantly reduced, and the consumption of extractant will increase. To weigh the advantage and disadvantage of EM, the value of EM must be between EM mean and 1, and then the optimal EM usually slightly higher than EM mean. It is similar to the EM for scrubbing. The optimum EM for scrubbing is slightly smaller than EM for scrubbing max. The graph shows the recovery trend at each stage in the simulated process for SMLU, LAND, LACE, LA, and PR at the organic outlet. So we can see from the graph, based on the recovery trend, it is observed that the behavior of separation and recovery of large fraction of A and B depends on the type of process control, either the extraction or scrubbing control. For the scrubbing control process, most of the recovery of A and B occur in the extraction and scrubbing stage respectively, and result for the extraction control process. From the graph, you can see that more than 50% of recovery of LAND and LA occur in the extraction stage, while 50% of the recovery of SMLU, LACE, and PR occur in the scrubbing stage. This agree with the data from previous table. The graph shows the recovery trend at each stage in the simulated process for Y, SMY, PR, ND, CE, and ND at the aqueous outlet. More than 50% of Y, PR, ND, and ND occur in the scrubbing stage, while recovery of 50% of SMY and CE occur in the extraction stage. This agree with the data from the previous table that Y, PR, ND, and ND are extraction process control, and SMY and CE, PR are scrubbing process control. The recovery trend of A and B is crucial to identify the manifestation of an ineffective separation zone. The occurrence of ineffective separation can be identified by the stagnant recovery after several separation stages in this proposed separation circuit, and an effective separation zone does not occur. The table shows the production output of LA, CE, PR, ND, and Y as well as their process parameter variable by using the proposed separation circuit. From the table, we can see the daily production of LA, CE, PR, ND, and Y. The mass flow rate of A and B in aqueous and feed was settled at 1.5 mole per liter and 1.45 mole per liter respectively to replicate the work of Zhang, Zhao, and Schreiner 2016. The separation was achieved by using mixer settler batteries, where the same size of mixer settler is used at 1.4 volume ratio of mixer to settler for each separation circuit, and the contact time was set at 50 minutes. By assuming 80% of the processing facility were utilized annually, so we can get the annual output for LACE, PR, ND, and Y. Nevertheless, this simulation separation process is lack process optimization attribute. For conclusion, Malaysian saprolite contains a significant extractable amount of rare earth elements which are at par with the other major deposits. It was shown that the proposed cascade fractional solvent extraction can be used to recover LACE, PR, ND, and Y from Malaysia's saprolite. The complexity in designing the recovery process for rare earth element can be simplified by having a specific recovery framework. Nevertheless, of rare earth element amount available in the sources, the ineffective separation zone is crucial to be identified during the process design stage to ensure high recovery can be achieved efficiently. Determination of production output can be used as baseline for further optimization.